To fly faster, higher, and more efficiently, we push the very limits of engineering. At the heart of modern aviation lies the jet engine, a symphony of power and precision. But to build one is to wage war against physics itself, starting with materials forged to survive an inferno. The journey begins not with steel, but with raw, unyielding ingots of titanium and nickel-based superalloys. Standard metals would warp and fail in the engine's core, where temperatures can exceed 2,000 degrees Celsius hotter than the melting point of the components themselves. These superalloys possess extraordinary strength-to-weight ratios and incredible resistance to corrosion and heat. Massive presses exert thousands of tons of force, forging these ingots into the basic shapes of engine components, aligning the metal's internal grain structure to build inherent strength before a single cut is made. From here, we turn to a technique with ancient roots, investment casting, modernized for the atomic age. For 5,000 years, artisans used this lost wax process. Today, robotic arms dip delicate wax patterns of turbine blades into a ceramic slurry, building a shell layer by layer. Once hardened, the wax is melted away, leaving a perfect, hollow mold. Into this, we pour the molten superalloy and employ directional solidification to create a single crystal blade. By eliminating the microscopic grain boundaries where weakness begins, we create a component immensely strong and resistant to creep, the slow, deadly deformation under stress. With the blade's core structure perfected, we must tame the heat. This is where advanced machining takes over. 5-axis CNC machines, guided by digital blueprints, mill the components to tolerances finer than a human hair. Then, high-power lasers go to work, drilling thousands of microscopic holes across the blade's surface. This isn't for weight reduction. It's a sophisticated cooling network. In operation, cooler air is bled from the compressor and channeled through these passages, creating a protective film of air that insulates the blade from the superheated gases, literally keeping it from melting. Now, the symphony of assembly begins in a pristine, dust-free environment. The engine is a masterpiece of for sections, suck, squeeze, bang, and blow. Technicians meticulously slot massive titanium fan blades into the central hub. The precision is staggering. If one blade is off by the weight of a paperclip, the vibrations at higher PM would tear the engine apart. Deeper inside, the hot section is assembled. Ceramic matrix composite liners are installed in the combustion chamber to contain the bang, and the high-pressure turbine is carefully integrated. Its sole purpose to extract energy from the blast to keep the entire system spinning. Finally, the marriage occurs. The core is mated to its nacelle, and technicians connect miles of specialized wiring. The beast is given a brain, the electronic engine control, or EEC. This powerful computer monitors and adjusts engine parameters thousands of times per second, optimizing performance, efficiency, and safety. The engine is now a thinking machine, but the masterpiece isn't complete until it proves itself. The finished engine is moved to a fortified test cell. Here, for the first time, it will taste fuel and fire. Spooling up with a deafening roar, it is pushed to its limits, while thousands of sensors feed data back to engineers. This is the ultimate validation. Only after passing this trial by fire is the engine worthy of taking to the skies, a testament to human ingenuity, ready to conquer the heavens. On this pristine, dust-free assembly floor, under the watch of massive overhead cranes, a marvel of modern engineering is born. This is where the core sections of a jet engine suck, squeeze, bang, and blow are meticulously integrated. It's a ballet of human skill and robotic precision, building the very heart of aviation. The assembly begins at the front, with the cold section. We see technicians carefully slotting huge, sculpted titanium fan blades into the central hub. The precision required is almost beyond comprehension. These blades are attached to the N1 and N2 rotor shafts, the engine's main rotating components. The balance is so critical that if a single blade is off by the weight of a paperclip, the engine would violently vibrate itself apart at the immense rotational speeds of flight. Every gram matters, every placement must be exact. From the cold, we move to the inferno, the hot section. This is where the bang is contained. Technicians install the revolutionary ceramic matrix composite liners into the combustion chamber. These lightweight, incredibly durable materials can withstand temperatures far beyond the limits of traditional superalloys. Next comes the intricate assembly of the high-pressure turbine. This section is the engine's powerhouse. Its blades must catch the torrent of superheated gas from the combustor and extract enough energy not just to survive, but to drive the entire front compressor and fan, keeping the beast alive. The climactic moment approaches, the marriage of the engine core to its outer nacelle. Once mated, the final, painstaking task begins. Technicians connect miles of specialized wiring, creating an intricate nervous system. This network all feeds into the electronic engine control, the EEC. With this final connection, the engine is no longer just a collection of mechanical parts. It is now a thinking machine, a self-regulating marvel capable of adjusting its own fuel flow and performance thousands of times per second. It is complete, a masterpiece of power and intelligence, ready for the sky. Assembly is complete, but the moment of truth has arrived. Before this marvel of engineering can ever take to the skies, it must pass a series of trials designed to find any imperfection, no matter how small. This is the world of non-destructive testing, where we hunt for flaws invisible to the human eye. Every single critical component is brought here to be fingerprinted. In this lab, parts are dipped in a special fluorescent penetrant. Under ultraviolet light, the liquid seeps into any surface-breaking defects, exposing cracks as thin as a single human hair. If a flaw is found, the part is immediately scrapped. There are no second chances. Other components are subjected to high-energy X-rays and ultrasound, allowing us to peer deep inside the metal itself, searching for the slightest internal void or imperfection. The principle is absolute. Safety is not a goal, it is a prerequisite. Once every part is certified flawless, the fully assembled engine is taken to the test cell-fortified concrete bunker built to withstand catastrophic failure. Here, mounted on a massive thrust stand, the engine will be brought to life for the very first time. Inside the control room, engineers monitor thousands of data channels. The air stills, then erupts. The engine roars to life, a controlled explosion generating immense power. The exhaust glows orange-hot as it's pushed to its maximum thrust. But it's not enough to be powerful. It must be resilient. The engine is subjected to the harshest conditions imaginable. We simulate a tropical deluge, blasting it with massive amounts of water. It's bombarded with hail, proving it can survive extreme weather. And then, the most critical test of all, ingestion. The engine must prove it can survive a bird strike, ingesting the object and shutting down safely without disintegrating. From raw sand and metal to the most complex and rigorously tested machine ever built by humankind. That is how we earn the right to conquer the skies. The engine, now proven and certified, is carefully crated for shipment, ready to begin its life on the wing of an aircraft, carrying passengers safely to their destinations across the world.